Before 1828, chemists assumed organic compounds possessed a mysterious vital force. That biological assumption was dismantled when a single application of extreme heat turned crystalline ammonium cyanate directly into white urea powder. This reaction proved that organic molecules did not require biological origins to exist. A compound produced by living things could be built entirely from raw, inanimate materials. In the decades that followed, chemists realized they could synthesize nearly anything. This triggered an explosion in laboratory synthesis. Researchers began mapping, isolating, and creating millions of newly discovered organic compounds. This massive catalog generated a severe data crisis. Common names provided zero structural information. Calling a molecule acetone identified the substance, but offered no hint of how its atoms were actually connected. To manage the sheer volume of organic chemistry, scientists required a deterministic algorithm. They needed a strict mathematical syntax where one structure generated exactly one universal name. This necessity produced the IUPAC Nomenclature system. The IUPAC syntax breaks molecules into 4 components: prefix, root, primary suffix, and secondary suffix. The root identifies the carbon backbone, while the primary suffix defines the carbon-to-carbon bonds, single anes, double enes, or triple ines. Establishing this root requires locating the parent chain. The default rule is to isolate the longest continuous string of carbon atoms, but that rule is subject to strict functional constraints. Consider this branched molecule. The physically longest chain has 6 carbons, but isolating it excludes the double bond entirely. By rejecting the 6-carbon sequence and selecting the visually shorter 5-carbon chain, the double bond is integrated. Multiple bonds strictly override physical length. Beyond the carbon backbone, a molecule's core chemical identity is dictated by its principal functional group. This group determines the secondary suffix. This priority table ranks carboxylic acid at the absolute top, cascading down through aldehydes, ketones, and alcohols. If a molecule has both a hydroxyl and an aldehyde, the hierarchy executes. The alcohol is demoted to a prefix, while the aldehyde claims the final suffix slot. This strict priority hierarchy removes structural ambiguity. By enforcing a single dominant group, the algorithm guarantees no molecule can ever generate multiple valid names. The prefix section acts as the molecule's coordinate system. It houses demoted functional groups, halogens, and alkyl branches. A 5-carbon chain with a methyl group and double bond shows numbering from both directions. Using the lowest locant rule, we force the lowest integer onto multiple bonds before substituents. Right-to-left numbering assigns the double bond position 2 instead of 3. Once the positions are locked, the isolated prefixes must be assembled into a final string. This process relies on strict alphabetical sorting. When arranging dimethyl and ethyl, the letter E takes precedence over the letter M. Multiplier prefixes like di, tri, and tetra are completely ignored during alphabetical sorting. The comparison is evaluated strictly between ethyl and methyl. The combination of lowest locant numbering and alphabetical sorting removes subjectivity. It yields an unbreakable, reproducible map of the molecule's exact topography. With the name established, the focus shifts to extracting the physical, 3-dimensional reality of the molecule using structural profiling tools. We analyze the degree of substitution by counting direct carbon-to-carbon connections. A carbon attached to one other carbon is primary. Attached to 2, it is secondary, scaling upward to tertiary and quaternary configurations. Alcohols and halides inherit their degree designation directly from the carbon they are physically attached to. If the carbon is secondary, the attached alcohol operates as a secondary alcohol. Amines are evaluated under different constraints. For an amine, you count how many carbons are directly connected to the nitrogen itself. The degree of the adjacent carbon is ignored entirely. We also assess the molecule's overall saturation using the degree of unsaturation, or double bond equivalence. This provides a mathematical shortcut to deduce how many pairs of hydrogen atoms are missing compared to a fully saturated alkane. The formula is straightforward. Count the rings and add the pi bonds. A benzene molecule contains 1 ring and 3 pi bonds, resulting in a degree of unsaturation of precisely 4. Calculating the total number of sigma and pi bonds around an atom dictates its hybridization state, operating in an sp3, sp2 or sp orbital configuration. This visual shows an sp3 hybridized carbon. To accurately map its true geometry, we translate the flat two-dimensional projection into a wedge-and-dash model. Solid wedges signify bonds protruding out above the viewing plane. Dashed lines indicate bonds receding below the plane. The IUPAC name isolates the connectivity. Pairing that name with the degree of unsaturation and hybridization parameters allows you to extract the molecule's specific reactivity and geometric shape in space. When chemists synthesize an unknown molecular structure, they rely on this precise algorithmic process to formally classify it. Let's run the raw structural data of a molecule containing both an alkene and an alcohol through the syntax engine. This 3-carbon chain encompasses the double bond and hydroxyl group, locking the root word as prop. Alcohol carries absolute priority, so we number right to left, placing it at carbon 1 and the double bond at carbon 2. These locants yield the final string, prop 2n1-all. Syntax locked, we map physical properties. The molecule has 1 double bond and 0 rings. Its degree of unsaturation is 1. The double bond carbons use sp2 hybridization, remaining planar. The carbon bonded to oxygen uses sigma bonds, forcing an sp3 tetrahedral geometry. The system functions as a deterministic algorithm. It translates complex molecular architecture into an absolute, verifiable structure, remaining strictly consistent across the global scientific community.